Right. Hello, everyone. Welcome to another session of the ongoing AFMS seminar series. It's my pleasure to introduce today's speaker, Professor Tad Truscott, who is from the Department of Mechanical Engineering at King Abdullah University of Science and Technology. Professor Truscott's current research interests are in fluid dynamics, novel imaging, and experimental methods. And he works on problems such as three-dimensional flow field dynamics of rising and falling bodies in water, acceleration-induced cavitation, the transport of water through desert plants, and the collective behavior of pelotons and fish. And today he's going to talk about large droplet formation and deep pool impact. Over to you, Tad.
Okay, thanks, Vishal. Yeah, I want to thank everybody for having me. I've actually never been to Australia, and this is the first time I've spoken Australia, so this is really cool. I'm really excited. I am an avid sailor, by the way, like I love to sail. And so most of the YouTube channel people that I follow are from Australia. So I always enjoy hearing an Australian accent, and I hope to one day visit. Anyway, I'm glad to be here today and to talk to you about some of my research. Again, we're going to talk today about large droplet formation and deep pool impact. And you can see some of these videos here where we're showing that. So in this central video, you can see a very large droplet. It's 60 millimeters in size. And to give you a sense of how big that is, a 2.7 millimeter droplet, which would be the capillary length of water, is on the left-hand side as a dot. And so you can see that after the splash occurs, there are droplets that are roughly that size. This is part of the reason why the droplet that comes down is so deformed, is because it is 60 millimeters. And one of the questions we're trying to figure out is how can we make droplets larger than the capillary length, and will a large droplet form a cavity similar to a small one? So those are the two questions we'll kind of answer today. And there's a little bit more on the along the way. On the right-hand side, you can see something also interesting. This is how we release the droplets, and I'll show you a little bit more about that as we go forward. And that's what you've been seeing here are three different size droplets being released from three different mechanisms. And that's an important part of what we'll look at today. Before I go too far, though, I just want to say, and Vishal gave me a great introduction, just kind of show you where I'm from. So I was born in Canada, actually, but as an American and Canadian citizen. I was educated at the University of Utah as an undergrad, and then I went to MIT as a graduate student. My advisor was Professor Alexander Tichet. I then went to the Naval Undersea Warfare Center, so I worked for the Navy for about a year. I then taught at Brigham Young University for 5 years, and then Utah State University for 6. And then now I'm at King Abdullah University of Science and Technology. I've been here almost 2 years. I have 4 grad students right now and 5 postdocs and a research scientist, and it's going really well. But if you're interested in postdoc opportunities, research science opportunities, or even graduate work, I'm super interested. I'm super happy to answer your questions and, hopefully recruit you. We have a very nice program here, and there are many, many opportunities. Okay, I've been sponsored by many different people, and I'm really grateful for that. This particular work is not sponsored by them. I have several collaborators you can see down at the bottom. And these are just some of my early works as a graduate student. I look a lot younger there. I was on Time Warp as a young researcher, and that was just a really exciting thing to do. I studied the water entry of spheres, but also of high-speed bullets as a graduate student, and that's what you're watching right there. This is basically my lab now. On the left, this is my lab back when I was in Utah, and this is a piece done by Wired Magazine on rock skipping. If you're interested, it's very, very well done, actually, by Wired Magazine, where I get to meet the world record holder for skipping. And I don't know if you know what the record is, but it's 88 skips on the water, which is just incredible. That's him right there. And then we used our high-speed cameras to test a bunch of things and work with him on some questions that we were trying to answer. And then this is my current lab here, and it's under construction. It's done now, but that's what you see. We have 3 main areas, as Vishal mentioned: 3D synthetic aperture imaging. This is a lot like tomographic particle image velocimetry. We use this in all kinds of aspects of our work, but tomography has gotten to be kind of like the mainstream. This particular method has some advantages, though, so sometimes we still use it, but we've also begun to just start using the algorithms and things that are out there from manufacturers as they've improved over the years. For instance, when Shake the Box appeared, if you know what that is, this really made it so that this technique wasn't really as necessary anymore. Here we have free surface impacts, and I'm going to talk a lot about water entry today. So what you're seeing on the left is a projectile. They're both, sorry, on the right, they're both projectiles, but the one on the far right here has a hydrophobic coating. And you can see that the cavity shape is different. The bubble that is formed as it enters the water is different and impinges on the surface of the projectile. So this is an important aspect of water entry. Here you don't have the hydrophobic nature, and so the cavity that makes this much different and smaller. You can imagine the forces on these two things are quite different, even though they're falling at the same speed and they're the same shape. I also work on these biofluids, these mosses. This is a really cool moss that lives in Utah in high deserts of the entire world. And it actually is called Centricia cananervis. And it can be dry for up to 70, even 100 years before it needs water. So that's really cool. And here you can see it's collecting water from fog. And then these droplets form on the hairs and then they move inward. Really, really fun work. And we're still trying to work with that here at KAUST. And then again, here's some swarming work. What you're seeing is about 50 pigeons flocking or leaving the ground. And we're using this synthetic aperture imaging in the upper left to dissect the flow or the birds. And you can see that I'm tracking their beaks here in red, yellow, and blue. So we do more than just that. We looked at pelotons and other things, but I won't talk about that today. Today, I want to show you a little bit more about the fluid breakup in what we call firefighting. This is our motivation really for why I would care to make a large droplet. So most of the studies in this area where people would study how the fluid would come out of an airplane and then form this cloud that you're seeing was done in the 50s and 60s. And this here, what you're seeing is this is a fire retardant, we call it in the United States. I'm not sure what you call it in Australia. It's red because it has a dye in it, but it also has a lot of salt. The salt causes the fire as it reaches it to absorb a whole bunch of the heat. And this is why it's called a retardant, and it's supposed to stop the fire. And it's also non-Newtonian. So as it hits the trees and leaves and ground, it's supposed to coat everything. And as you see, one last thing I wanted to show you. When it comes out of the airplane, you see that it really, when it hits the ground, the idea is that it looks like rain. And a lot of it is kind of coming down like rain, but you see that it's still kind of clumped together. And the methods that they check these things with are quite old. So what we wanted to do is work with computational scientists as well as ourselves, experimentalists, and see if we couldn't improve on this. One of the biggest problems they're having is that every time they try to make one of these lines, they sometimes have to have the pilots fly by 4 or 5 times to do it. And this is a jet, no longer a propeller. So the old algorithms are kind of not as relevant, but in addition, they don't use any targeting systems like they do in the military. So that doesn't help. It makes it very hard. And you can imagine trying to fly a plane at 200 miles an hour, a big jet, only 100 feet off the floor. That's really scary. So they miss a lot, and that's expensive. So we were asked if we could help build something that would allow the pilots to have a heads-up display. And this is just kind of we'll kind of keep going here without the motivation. We'll kind of move into the more specifics. Here's some drawings that were done in 1973 by Swanson. I kind of like these. I don't know, I'm not sure they're really accurate with today's CFD and high-speed imaging, but it's not necessarily wrong. What we're trying to do here is you have the tank, you have this fluid coming out on the right-hand side. You can see you have the onset of what we call Taylor instabilities. This is basically the stripping, a lot like a Helmholtz instability. Then you have these thin amounts of breakup and you have continued stripping of the fluid. These stripping of the fluids end up in fairly large droplets, I'll call them for lack of a better term, but this is still breaking up. And then you go to this point here, which has been studied quite well, where you have the very small droplets, maybe some medium size. These both would be in the capillary range. And then maybe some that are on the high end of the capillary size, so more like 3 to 4 millimeters. So we'll look at 3 to 4 millimeters today. Rain is typically somewhere between 3 and 4. The largest rain droplet ever recorded was 8, but we will be looking at all the way up to 60 millimeter droplets, but they'll be, because we're looking in this green region for where breakup occurs. This is kind of how it's done right now. they take these airplanes, they drop these lines over on top of these fields, and then they take measurements to determine how well done the coverage is. And all they do is the fluid basically falls into these buckets. But as you can imagine, if the fluid is coming down too quickly, it can bounce out. You can see they've been doing this for a really long time. This is a study in 1973 from near where I lived for a long time. And this is a study in Montana done maybe 3 years ago, I think it was. And they basically label all of these buckets and then put it all together. And when they do, this is what they get. They get basically the length of the drop in feet, the width of the drop in feet. The airplane is traveling from the bottom to the top here, even though I have this picture. This is from an AFRJ 85, for instance, at 1,254 gallons per minute. The velocity is 130 knots and the height is 205 feet off the floor. And you see what the coverage looks like, anywhere from 0 to a 10. And they have their own way of explaining what this means, but basically just think of it as like millimeters per cubic meter or something like this, okay? Anyway, on the right-hand side, this is interesting, same jet, almost the same, a lower flow rate, 132 knots and then 176 feet. And sure enough, this is what we would expect. We would expect a lower coverage. That's great. But sometimes they have the exact same one. So here we have 298 gallons per minute, 130 knots, 167 feet. And the one on the right is almost the same. It's only 10 feet higher. And you can see that the amount of coverage is actually quite a bit different. And so they have a lot of variance. And this is part of the problem as well. So each flight is $25,000. You can imagine if you have to do that 5 times to get one line, one important line, that becomes quite expensive very quickly. So the idea was, let's try to model the fluid dynamics in a better way. Also be able to come up with some quick modeling so that like a heads-up display doesn't have to solve a whole computational process, or you'd have a lookup table or some sort of AI to make decisions for the flight, based on crosswinds, based on height off the deck, and maybe even some sort of like alignment with like a laser system that maybe one of the ground crew has, okay? So that's nice. And in order to do that, the first thing we thought of is, okay, we've got to start looking at what happens to these larger droplets as they start to break up. So this has been looked at for quite a while, at least the smaller droplets have. You can see the work of Villermo here. This is a wonderful review in the annual review of fluid mechanics. You can see how a droplet will fall. If it's a little bigger than the capillary length, it will come down and then eventually it will form a bag and then the bag will break up. And this is what is thought to happen to most largish droplets as they fall, especially in a lab setting, okay? But then you have Bormann, the work of Bormann. This is a group out of Germany. And they show that there's a couple of interesting things. One is that the droplets are not spherical and they're not teardrop shaped. And so these are real droplets in experiments that are done in the field. And these are what they think rain droplets really look like. And then the work of Villermo also sort of has this gamma prediction of what the distributions might look like for droplets that are falling from the sky. So we kind of need that. The other thing we need to know is that they oscillate. So here's what the axis ratio would look like versus time. So this is the work of Bormann here again, and this is well understood. And even Rayleigh did some of this work. This here is also Bormann, but this is also the work of Rayleigh, these theories that came about, which basically just says that the frequency of oscillation of a droplet is very dependent on the drop diameter. So here we're looking at the 2-0 mode, for instance, in the black line. I'll show you what that means in a second, but basically you can see it matches quite well with the experimental data that was taken, and it matches with ours too. Okay, so just so you can kind of understand how breakup can work and the different types that there can be, there's what we call vibrational breakup. So this would be where you have a droplet, it's perturbed in some way, and if it's large enough like this, but also small enough where you have the Weber number be less than 12, then it will basically form into multiple droplets. This is that classic problem of a cylinder of fluid breaking up into many droplets. Then you have this critical breakup morphology when you have bag breakup. This is when you're in a Weber number between 12 and 50. And this is the classical one that Villermo showed where it forms a bag and then breaks up. But you can also get multi-mode breakup. You can get sheet thinning breakup. You can get catastrophic breakup as well. And these are all based on the Weber number. So if you look on the right-hand side, you have these critical Weber numbers. We have 3 different lines for the 3 that I'm kind of outlining on the left here. Today, we're going to focus down here on the bottom because we're going to have such large droplets. But you can see that all of this is also a function of the Ohnesorge number. And we have another paper about this, and it looks more at this particular issue of how breakup occurs. We have an ongoing work as well where we take droplets that are non-spherical, because most of this work over here was done with spherical droplets. And as they're non-spherical, you actually can bump yourself into these different regimes, even at lower Weber numbers, but that's for another day. So anyway, we're going to look at this, and what I kind of put together is this to kind of help you see where we're going. So what about large droplets? Okay, so if you are to look on the bottom, this is our diameter of our droplets in millimeter, and on the left is our velocity. And the first thing I want to note is that we have our critical velocity here is the dashed line. Okay, so everything above that would cause breakup. This would be a Weber of 13 or more is in the blue. And then what we would assume we would get basically no breakup on the bottom here. On the right-hand side, we have the drop height. So I'm also trying to show this in terms of drop height. But if we just focus on velocity for a minute, you see the dashed line here is what we would get for the terminal speed of a droplet if it were to allow it to grow and flatten, because they tend to flatten. If we didn't let it flatten and we assumed it was rigid or a sphere of the same density, we would get the black line. And this is, not real. This isn't what happens. As the droplet grows in size, we get a flattening. And so we get this other dashed line. And what you see is if you're below this line, you don't have any breakup. But the problem is that most of the experiments, you start to get around here, a little bit above this line. But our objective is to go even further into this regime here. And what it means basically is that any of our droplets should probably break up, even though here in this theory, it says it should happen at 12 or 13 millimeters in diameter. What we find in practice is that breakup usually is occurring somewhere here where the red line is of around 8 millimeters is where breakup will occur. And so we're gonna go into that and talk about that. All right, so here's some oscillations just so we get back to the modes we were talking about before. Today, we're really going to focus on the 2-0 mode, which looks like this here. So it's sort of like a donut, and then it grows into maybe a rugby shape, a rugby ball shape. So donut, rugby shape, rugby ball, something like that. But if you were in the 2-1, you get an oscillation that looks like this in both axes. So it's basically still a two nodes, but then it's off axis. So that's what the 1 represents. So Lord Rayleigh sort of put this together in 1879. He said you'd have R, which would be a function of N and or call it N and M, and a function of time, theta, and phi. And this is basically what the estimate would be for a spherical perturbation. And he said that this would be related to the diameter of the droplet, and indeed it is. There's some other ones here that are important, like the 3-0 and the 4-0 mode, and you're going to see some of those today, but the ones that we're really interested in are 2-0, and that's because we're exciting this droplet in the 2-0 mode. It's also the one that is the strongest. It will have the largest amplitudes will be in the 2-0, and that's true for all droplets, and that also fits with Lord Rayleigh's and Propaker's theories. Okay, and this happens even for small droplets. Here we have a radius of 1.8 millimeters. That's pretty small. And these are capillary droplets coming from a needle. So if you do any work in this area, or you watch your kitchen sink droplets, or you use a needle and get droplets to come off of it, you'll always have some amount of oscillation occurring. It will dampen out pretty quickly if it's a small droplet, but it does occur. And so again, it's important to remember this. And this is kind of, like I was mentioning earlier, a little bit more of our future work, but you'll see all of that as we go forward here. So these are some images from our experiment, everything from 0.3 milliliters up to 2 milliliters. And you can see that they're mostly in the 2-0 mode. These are just some crops I kind of wanted to show you of what some oscillations look like. And I call these pendant drops, but they're not actually pendant drops. These are dropped from our apparatus, which I'll show you in a second here. Okay, so here's how the experiment works for these larger droplets. We know we need a different kind of surface to release them. We can't release them from a needle because the capillary length has been exceeded, and so the needle won't be able to hold that much fluid. So we have to put them on a surface and release them. So Jeff Fonnesbeck, one of my master's students, built a bunch of different surfaces and then tried to release the droplets. And here it's being released from a basket, and you can kind of see how funny it looks. There's a little droplet that went flying, and it has some elongation to it. And these are all issues we have to face. But what we do is we release it with a solenoid, and then the hope is or the idea is that it will move in a radial direction faster than the droplet because of gravity. We can also add an elastic spring and things like that. We can also move the mass further away from the ball bearing, all that kind of stuff. And so we do a little bit of that and get some results. We have multiple cameras that we needed for this. Our future work I'll talk about in a bit, but right now the way we did it is we had 4 cameras in a row and they looked at about 1.5 meters. There's a light bank here, so they're being backlit, and we're having to use all 4 cameras kind of in series, but they're all synchronized, so it's fine. Okay, and here are some of the geometries that Jeff built. You can see, here's a picture of one. It's just a kitchen sink mesh he found. He wanted to try this one, for instance, and this one actually works really well, which was super surprising to us for some droplet sizes. Here are the flat cases. So if you imagine this is like a piece of aluminum made flat, this is what the droplet might look like on top of it. We then tried different cone angles, beta, and then we also tried to make these grooves of spherical size R in the flat plates as well, just to see which one of these would work best. And these are upside down. I apologize for that, but these are the 4 different shapes that we got and sizes of the meshes. So this mesh here on the left is actually represented here by small sink mesh. And you can see how big they are. They're much bigger actually than our flat plates. And so I'll show those. Here's a picture of them. Some of them are purchased and 1 or 2 of them were made. I don't have a picture of the ones that were made here. Then we coated these. All of these are coated with a hydrophobic coating. And in general, our wetting angles are about 120 to 140 degrees C. 160 degrees. I forgot. We used the Glacomer Zero Coat in our last experiments, and so they're a little bit higher. Sorry, originally we used a different coating. Okay, and so here we're going to talk a little bit about the tracking. So we have the droplets falling, remember, and we basically take the droplet. You've probably done this before. It's becoming quite common in engineering to do these types of things. But basically, you take the image in, you threshold it, you get a black and white image, you then find the edges, and that's what we do in time. You can see us doing that in this video here as well. What happens at each moment in time is you have a Y and an X position. You can see here we've taken all those and made them as these red dots on the outside line here. We call negative 0 to negative X and Y equals 0 as our datum, and then we have theta that rotates around this position. Then if we plot theta versus R minus the R mean, so this is our mean minus whatever data point we had out here at the edge, then we get these types of plots, which is quite helpful. We take these plots on the upper right, and then we stack them for every time series, and we color them by height from minus 20 to 15 here in blue and yellow. And then you can see what the droplet kind of looks like if we unwrap it, what it looks like in time. And that's really nice. We can then take the FFT of it, and we get theta versus frequency. And you can see here for this droplet, you get a frequency around 2 hertz, and its highest peak is around minus 1.8 radians and 1.8 radians. So it's really quite useful, and you can kind of, from this data, you basically know the shape and you also know the frequency. Okay, this is just to show you how repeatable it is. These are 3 cases that we used on the left, and you can see that this is the 3 cases on the bottom, and they're very similar. Again, we do that for the right-hand side for a different case. You can see it's very repeatable. They look very similar, and they're indeed 3 completely separate tests. So it's very repeatable apparatus. And this is kind of what it looks like from all 4 camera angles. Here's one that we're dropping. It's a about a 2 milliliter droplet, which is roughly 10 millimeters in size. And the release acceleration is about 1.2 Gs. And you can see that we've incited some sort of Rayleigh frequency where it's oscillating, but it's also almost pinching off, you could see. Here we have a little bit the same droplet, but we've increased the acceleration to 1.6 Gs. And here you see that it's the same plate that we used. You can see that the droplet was elongated so much that the Rayleigh plateau instability was incited, and the droplet was pinched off and separated from the rest of the group. And this one we would call, basically we would end it there, and we would no longer study it because this is what we're trying to avoid. What we were trying to achieve is get a sphere falling as a perfect sphere, and then see what happens in time and use that. What happened instead is we were able to basically sort of control the shape, but also we were able to delay its ability to flatten out. And so you'll see some of that in a few minutes, but what you're seeing here is if we use a basket, we can actually start to match the curvature that we want with the droplet. And if we match the acceleration, we can get droplets that appear as roughly spherical, very close to that. The basket also has another advantage, and that is that it releases the sphere extremely quickly. So this is something we're still working on before we publish this. We're almost done with it. On the right-hand side, you can see that there's a release time associated with the droplet. And so there's different shapes you could use to enhance the release to be more spherical. And on the left-hand side, where the release is very quick, you can be a little bit, well, indeed, again, you have to kind of think about what the shape might be for every single droplet volume. And so that's the thing we're doing now to wrap this up, is connect this to the theory. And we have some 3D printed baskets we're now using. There's an aspect ratio associated with every droplet. This is basically its height to width. And as it changes, you can see in time here. It also increases with diameter. So as we increase the diameter, our aspect ratio increases. And this isn't necessarily a good thing. This actually makes it more difficult for us to, and one of the reasons why large droplets don't really exist in nature very often is because when they do form, they get these high aspect ratios and then they pinch off and they form many smaller droplets. And we've gone through this already. So what I wanted to show you is if you had mesh surfaces, we have these 4 different mesh surfaces on the left, these ones here. And then on the right, we have these 2 solid surfaces with 2 different amplitudes. What you can see is that this droplet, for instance, this particular droplet that we're looking at, which is the same size for all of these pictures, the best and most spherical one for that one is going to be this small sink mesh. And you can see that in the, it's visually obvious. The E is actually not too bad either, but it's not as good as C is here. And so what Jeff was able to do is sort of plot all of that in this way. And what you can see is that if you have a small droplet, so 0.34 milliliters, these are droplets that are basically of the capillary length, then any of these flat plates and even some of these meshes are basically going to give you the same response. So that's great. However, if you're going to have large droplets like the 2 milliliter one, which is basically 20 millimeters in diameter, then the best case you can have is this SS20 mesh, and it's over here. Otherwise, you get much worse response from that. So it's really quite cool to see this. So on the top, we have the 0.34 case you're comparing, and on the bottom, we have the 2.08 milliliter comparison. And you can see the lowest amount of oscillations occurs here in this case. So that's really helpful. We can also look at the frequency content of this, and you can see, as we would predict, the smaller droplet has a higher frequency of 45 hertz, and the larger droplet has a lower frequency of 2 hertz, and that fits really nicely with the Rayleigh prediction. Okay, so to get into the last part of the talk here, I want to look at what happens then if we take these large droplets and use them in all kinds of conditions. And here we're going to use the large droplets to fall into a deep pool, as I mentioned earlier. And again, just to remind you, this is a droplet of 60 millimeters falling into water. So it's water on water. You can see some really cool stuff happening. The droplet is not exactly spherical, so that's cool. You can see how big these cavities are. They're really quite large. This is 6 centimeters. This line here is accurate to the sizing. You can also see that there are these many bubbles entrained below the surface, and that the jet that's formed is probably what you might want to call a Worthington jet, but it's extremely thick. It's a very large Worthington jet. And there's also a bubble in the droplet somehow has gotten in there, likely from some sort of oscillation. And that droplet forms an interesting bubble pattern below that we won't talk about today, but these are all just interesting features to mention. So again, the background is basically the same as I mentioned earlier. Here I'm saying raindrops size is usually less than 8 to 9 millimeters. Those are the maximums. And the capillary length for water on Earth is 2.7. And why would you want to study this? Well, you have things like sea wave breakup. They don't have, a lot of these waves don't have time to form into the smaller droplets. So the larger droplets would be good to study. Again, firefighting was another, and actually planetary impacts. This is an interesting paper in 2021 where they use filled balloons that they pop just before entry into the water. But what I didn't realize until I met these people, I didn't realize that when two planets collide, or like a small moon and a planet collide, even some asteroids, they're both basically liquids. If you assume they're both liquid-ish, you can actually get very accurate results. So they use a target liquid and an impacting liquid, and they study that and get very useful information. So that's kind of cool to have it have that kind of an impact. And they've looked at our work from some of the other previous things that we've done, but I think this is a really cool connection. All right, here's the experiments. You have the droplet. We're going to drop onto a water tank. The water tank's about 40 centimeters high and about 40 centimeters wide in both directions. We have a light that will be on the right-hand side with a diffusing screen, and then we'll use 7,000 frames per second to capture this. And then here are some things we'll have to look at. We're going to have our axis ratio is going to be very important here. So we'll have A over B. A is the width and B is the height of the droplet before impact. We usually look at the axis ratio right before impact. So here it looks like we're looking at it several centimeters above the surface. That's not true. We're doing that right before the impact is usually where we're interested. And then in the water interface, we're going to look at the cavity depth, H max. And at H max, we're going to measure the width of the cavity, and we're going to call that D max. And we're going to look for its largest diameter. So that will give us a cavity aspect ratio of H max over DH max, and this will be the maximum of this particular behavior. A couple more things. We need to know the Weber number, which is basically just the velocity squared divided by surface tension, and the Froude number, which is again velocity squared, but it's divided by our gravitational forces. If you're into hydrodynamics or naval architecture, you would suspect that the Froude number would be important, and maybe the Weber, because these are kind of small, but they're also kind of large. So maybe you would think you could ignore this, but it turns out it'll come back to us. But if you see here, we plotted the Weber, let's say, versus the Froude number. You can see that they don't collapse necessarily on one another, but you see what happens as you increase D naught, or the size of the droplet. D naught represents the diameter the droplet would be if it were a perfect sphere. And we're going to use that several times throughout the study here. So this is a look at some work that's been done in the past. And what they notice is if they take H max over D naught, and that's basically, how deep does the cavity form? And then you plot that versus the Froude number. Here they're dividing by rho prime, which is just the density ratio. What they find is they have this theory by Leo in 2001, but the least square fit fits a little bit better from the same study. What you notice is that the data is kind of scattered. It kind of pops up and down here as it's going with the Froude, and that's fine. The other thing they notice, here's some pictures from those same types of studies where you see the fluid causes a deformation in the surface. The surface becomes what I would call hemispherical. It looks very beautiful here. And then as it collapses, there are some capillary waves that form on the surface, and that's what you're seeing is these waves here, and then it'll form a Worthington drop. What's interesting, though, is if you take that same H max as a function of time, what you see is that for every different case, so you're increasing the diameter, let's say, or the Froude number here, what you'll see is that as Froude increases, the depth of penetration increases. And so that's what we would expect to happen if we keep making larger and larger droplets. But what we see is on the right here, this is the same data, our data, I'm sorry. These droplets out here are near the capillary length, and they fit quite well with what Leo showed in their work. However, as the Froude increases because of diameter, notice that we actually are not, we move over into this region. So these cases over here are the largest droplets, and they don't behave like we would have expected them to on the plot. So for large droplets, cavity height decreases with increasing Froude numbers. So why? What is different about these large droplets? And the different piece is that there's these oscillations, but the oscillations occur for the smaller droplets as well. They're just not as large, right? The aspect ratio, like I mentioned earlier, is smaller. So when your aspect ratio becomes more extreme, then it makes sense that it would play a larger role in what's happening. So if we look back at Rayleigh's model, We choose mode 2.0. Our data fits very well on this. You can see that here. So this is our data now. And then the line is the Rayleigh, and then some other past data as well. It fits decently on that line. So that's good news. But what we see is if we take a large droplet, we oscillate it, we notice that it has three different types. Okay, we have an oscillating regime. So if it's this is a 2 centimeter droplet or 20 millimeters. We notice that as it's falling, these are all different Weber numbers just before impact. We notice that we would call this an oscillating regime where you get spherical, then flattening, and then maybe more spherical again, and then flattening. So this droplet is on the verge of wanting to be completely flat, but doesn't quite make it. Here we go with a larger droplet, 3 centimeters. And you can see that this is what we call the flattening regime, where it's oblate here, but then it becomes very prolate very quickly with higher Weber numbers. And then we even get into the bagging regime, which is what we expected way early on in the presentation. We talked about this, but if our Weber number gets higher and higher, we're going to get into the bagging regime. Okay, what we can now look at is the access ratio. And so for this oscillating regime, we're around 1.5 to 2. But if we start to get larger and larger droplets, we get into this flattening regime, and you can see these curves just kind of move upward from, an access ratio of 1, let's say, up to 4, 5. And then, of course, at that point, they're probably going to break. And so this is the effect we have to include. Here's some evidence of that. If you have a Froude number of, say, 40 and it's prolate upon entry, you're going to get a very deep cavity. I'll show that here. It's about to happen. And these will play twice, so it's okay. So here you get this nice deep cavity, which makes a lot of sense. You've got a long, narrow, projectile-like droplet. It makes sense. And then on the right-hand side, as you go up in Froude number, you're going to start to get, this is a nearly spherical droplet. So let's go back. You see this droplet is sort of spherical, and it creates this shape. The one on the middle here is quite a flat droplet. And so you're going to get this nice flat shape. And then the bagging case is interesting. You're going to even form a jet before you have collapse, which is cool, and we'll talk about more. But it's also a flatter cavity shape. And so again, this doesn't, if we want to be able to scale this Hmax and Dmax with something about the entry of the droplet, we can come up with this, which is pretty simple. We just have Hmax over Dh, and then divide that by our aspect ratio. And notice that it fits pretty well. These would be oblate shapes on the left of less than 1, and then prolate shapes on the right hand greater than 1. And prolate shapes should make deep cavities, and oblate shapes should make shallow cavities. That's great. So we show that that works. But what if you want to scale all the data together? Well, you probably could use an energy balance, as we've done here. So use a droplet kinetic energy on the left is equal to the maximum potential energy of the cavity on the right. Here we have the V is the impact velocity, Hmax again are defined. If we solve for Hmax Dmax over 2AB, we get some constant out front, which we call the splash loss. It's coefficient. But what we are able to do is show that the Froude number, if it's scaled by B, so the height of the droplet, not the D naught, but the height of the droplet at impact, then we're to the 1/2 power, then we're actually able to come up with a little better scaling. So we have Hmax, Dhmax over AB here on the bottom, and then we have that Froude number to the 1/2. And what you find is you find a better scaling for all droplets, and that includes both the capillary droplets done in the past, as well as the much larger droplets that were done now. So basically for droplets that D naught is greater than the capillary, the maximum depth of the cavity scales with Froude B to the 1/2. So that's kind of nice. And we think that it might also be part of the reason why these droplets over here, they don't scale quite like the theory would estimate. The theory uses spherical assumption, and so they would be obviously lower than that because of the flattening. But remember, these droplets also oscillate, so it's probably likely why they're on both sides of this curve here, and they don't have such a smooth shape, is because of that oscillation that occurs. Just a slight oscillation will change the cavity shape just a little bit and change Hmax. And so that's an important aspect of this that we have to consider, especially if we're going to be looking at larger droplets, say in the ocean. So just a couple of last fun points here. We also notice that when the cavity retracts, we get a thick jet, which emerges out of the pool I mentioned earlier, and it decays without forming necessarily a second droplet. So here's a case here where we zoomed into the top. It's cut off here. I apologize. But the droplet is not formed, like in the case of the Worthington jet. And it's also interesting that we have the simultaneous development of the jet and cavity. We're looking into that as well. And this comes from this bagging regime. So to conclude, just really quick, we can make large droplets repeatably and minimize amplitude, but the apparatus has to be carefully adjusted to accommodate acceleration and geometry so that the shape that you want to form is made. So in our case, we wanted to make a sphere. This one is not doing a great job of it, but we have others that do. And in order to form those, you have to consider acceleration and geometry. And that geometry is related to the release of the contact angle. And then just a couple other things that large droplets, they oscillate or flatten, which gave us some sort of insight into some of the penetration depth questions people have had for a long time with droplets, and showed that prolate droplets increase the depth and oblate droplets reduce the cavity depth. So we need to take that into account and come up with a different scaling. And here it's basically also Froude number to scale it, but we're scaling by the height of the droplet at impact to the 1/2 power. So a couple of future directions. We want to do this with non-Newtonian flows now, and we want to experimentally observe how breakup changes with droplets that are larger than the capillary number. We're doing that still. There's a few more questions we want to answer, especially this one here. We want to look and see if we can find Weber numbers that are a bit higher and move into those regimes from this natural falling piece to see if that happens in the fire retardants. One of the ways we're going to do this, I'm sorry about this image here, but we have a drop tower we've built. This is our preliminary drop tower. We're just finalizing it and rebuilding it in this room and attaching it to the wall. And we'll be doing those experiments this summer. And we also work with the numerical group, Somduta at Utah State and his lab. Here we look at how does aspect ratio affect breakup? And our preliminary work is showing that it does depend on the phase. This is just an example of the model that they use to do that. And they've already finished most of their work and shown that this is the case. And we're working towards trying to get that drop tower working so we can support the work with our experiments. And with that, I thank you so much, and I'll take any questions.
Thanks, Tad. Excellent visualizations there. Very interesting.
Welcome. Thank you.
Right. I'll open it up for questions. If anyone has any questions, please feel free to unmute and ask, or I'll type it in the chat and we can read it out.
Hey Vishal, can you hear me?
Yes, Daniel, go ahead.
Hi, sorry, I can't. My video is not going at the moment. The sound's probably not very good. Thanks, Tad. That was really interesting. This is Daniel Duke from Monash Uni in Melbourne. I'm just interested. I'm interested in the role of turbulence on droplet breakup because I do a lot of work in aerosols and sprays. Have you? And this is probably relevant when you're looking at the firefighting situation, I would think, in terms of Reynolds numbers. Have you done any work looking at turbulence in the gas phase, or are most of your Reynolds numbers relatively low and your droplets are quite large?
Yep, good question. So our Reynolds numbers are fairly high, I believe. So, and maybe Daniel, maybe you know this, but the Ohnesorge number is usually something that is a bit more relevant to the droplets if you're interested in the breakup, because you have both the Weber number included and the Reynolds. So that's a great question you're asking, and I can see why you're asking it. Yes, so in our case, no, right now we drop these in a roughly quiescent airflow, but that is only temporary. So with our drop tower, we plan to also put heated surfaces below and maybe even flames for the droplets to fall into. Those are some questions that aren't necessarily related to wildfires. They're more in buildings, but there are a lot of studies missing there are a lot of CFD actually that could benefit from that particular piece of information. In addition to that, we do have some people here that work in atomization. And so they do look at this turbulence piece external to the droplets as they're breaking up, but I don't have any experimental work in that area as of yet.
Okay, thank you. Very interesting presentation.
Yeah, you're welcome. I am interested though, so if you have a specific case you'd like to study, I'd be super interested in discussing it further. We're always looking for more things to do with these large droplets, because I do think sometimes when we're able to look at it in a different way, we find something that maybe we missed when we were looking at it, say, at a smaller scale. But that doesn't mean we can't do the smaller scales. Just that's something that we've been thinking about.
Sure, yeah, I tend to look at droplets that are on the very small side in aerosols, and we're quite interested at the moment in looking at the role of turbulence intensity, particularly on the secondary atomization process. But maybe I'll get in touch with you another day about that. Thanks.
Yeah, you're welcome. That is cool.
We have a question in the chat. I'll just read it out to you. It's from, I believe, Leo. Have you been able to keep the Weber number and the Froude numbers the same, but change the shape of the drop at impact?
Yeah, that's a good question. I think the answer is yes, but it's been a couple of months. Let me just look really quickly here. I think you guys can still see my screen. Is that correct?
Yes, we can. Yep.
Okay. Yeah, I don't show it here, but we do have some cases where we kept the Weber number the same. And the food, let's see. Yes, we do have some where they're similar, I guess would be the answer. Unfortunately, we don't have, as of yet, without the 3D printed perfect control ones, so these are close, but they're not quite, they're repeatable, but they're not exactly where I get to choose what the final shape is. I would say we're close, but not exact to that. So we do have some where we have the same Weber and the same Froude with two different shapes, but it's not like we're able to do that for all Weber and Froude numbers.
Right. Tad, what is the Australasian number for these droplets that you had?
The Australasian number for these droplets is, let me see, that's a good question. I can't remember. Sorry, I don't have that. I have to look. I don't remember.
But I believe that will definitely be much greater than 1, right? Because they don't have the propensity to form.
Yes, they're definitely
yeah, okay.
more than 1. I think this might be a little bit off. I probably should have this be more like this, actually. And yeah, something like in this range. Yeah, maybe 10 to the -1, maybe, but definitely, definitely true.
Okay. Yeah. Okay.
It's a great question, Vishal. I might check. I'm gonna fix this today. That's good point. Yeah.
All right. I was just wondering, what's the fundamental reason behind the oscillation of those drops as they leave the nozzle? Is it more because of the interplay between the surface tension and the ambient?
You're saying like the ones that were on the needles? Is that what you're saying?
Yeah.
Oh, sorry. Let me find those. So
I mean, any at least I think in the initial slides.
Like these ones here, like this? Is that what you're saying?
Yes, the oscillation, the oscillation frequency. So what's the fundamental reason for those oscillations?
Well, first of all, it's kind of like in a solid where, like, if you were to ping it with a delta function or, just something like that, you're going to get a natural frequency. So 2.0 happens to be mostly, typically it's the natural frequency of the most common natural frequency of the droplet or a spherical shape. So that's why you get 2.0. And then in our case and in the needle droplet, you can see here that the pinch off occurs at the top. And so now you have a deformation of the top. There's a slight deformation of the bottom as well. But as the top tries to recover from that, that's what causes the initial 2.0 to occur, is that it's in that axis, So if you did this in space, I don't think you'd get necessarily the exact same. In fact, it'd be tough, right? Because in space, you wouldn't really get it to release. It would just keep growing in size, right? So these are all kind of interesting gravitational aspects of it as well. And the capillary length is governed by gravity too, right? So this is part of why this occurs.
Right.
Yeah.
Okay. I was just trying to understand the reasoning behind the mechanism, the release mechanism that you have, because you kind of hold the drop and then have the sieve moving instead of actually releasing the drop from the top, maybe from a syringe or some nozzle. Why have we chosen that?
We're making it worse because it's a flat plate, and that's kind of why this study kind of got started. Is like, it doesn't, you can't hold a droplet with a needle any much larger than the capillary length, and so we wanted to kind of keep making bigger and bigger droplets, especially for the non-Newtonian stuff we're doing now. And along the way, we discovered that it's just really hard. You can't just put a pancake droplet, which is what it's called when it's on a flat surface and it's large. You let that go and it just doesn't really stay together.
Yeah.
And so this is why we started, the student was like, it was actually Jeff's idea. He was like, I think we could maybe force these to be a different shape. And I was like, yeah, okay, go ahead and try. And in my mind, I was like, I don't think it's going to work, but it started working. And then we started to think about it. And a lot of it has to do with this release speed. So, here you can see that there's the contact angle, receding contact angle is important here. And so coupled with the acceleration and the difference in velocities between the two objects, the plate and the droplet, that's how it wants to release. So air has to basically get under the droplet. And in order for that to happen, the receding contact angle has to be exceeded. And then the droplet wants to return to some sort of angle like below that. So that's kind of where this comes about. We have a new shape that we've developed based on that in a mathematical model. I just wasn't presenting it today because I don't have a lot of droplets from the model yet. But we've developed it. And then the basket one is actually even better because you can just pick the shape you kind of want because release happens so quickly. The only disadvantage is you have a lot of high frequency content from every single one of the small holes. But those high frequency pieces go away so quickly because they're not in the natural frequency zone. So you can ignore them almost. So this is why this works quite well. And I think for the community, this is kind of cool. This is like a really helpful thing to know if you want to study larger droplets doing different things. This is kind of why we kind of moved in that direction. We'll keep going in it, but yeah, it's cool. Yeah.
All right.
Is this
great?
JL Leo here, the person that asked the question? Is this isn't the author of this this other work, is it?
I don't know. We'll just wait for him to respond.
By the way,
yes. He says yes.
That's fantastic. And by the way, this is fantastic work. I didn't express that as much as I should have, but we have loved it actually. And the theory that we're making, that you have done, we're using to try and redo with an oblate or an ellipsoid, basically, instead of the sphere that you guys used. So if you're interested in chatting with us, we would be super happy to have a chat, get your opinion, your thoughts. Yes, okay. Yes, that makes sense too. And maybe I can ask, since they're here, what do you think? Do you think that there was a chance that some of this discrepancy is because of the oscillation that's not taken into account in the model? Or do you disagree with that? What do you think? This is so exciting. I can't believe this. That's awesome.
We'll just wait for Leo to type it.
Okay.
Any other questions in the meantime?
I maybe have a question. I'm Joey Furman. I work on ocean waves. So I'm glad to see some breaking waves, or at least a picture of it as well in the presentation.
Yes.
So one of the things that's important in our case is the small droplets that are produced when the waves are breaking. So you have you talked about the very big droplets, but have you been looking at how many droplets and how small the droplets are that are produced afterwards, or is that not really something you've looked at so far?
No, that is certainly something we have started looking at. So we have 2 side projects. But let me understand first what you're saying, because as an ocean researcher, we would like to know more about what you're interested in. So you're more interested in not the breakup as it's coming down, but after impact, those droplets and how many and how big and all of that. Is that correct?
Well, the thing we're most interested in is the heat flux that is caused, and the very big droplets, they drop so fast into the ocean that the heat flux is probably negligible. But the smaller droplets that are produced afterwards, they can actually really change or enhance the heat flux from the atmosphere to the ocean and the other way around. So that's something we're interested in. Yeah.
So when we did this study, one of the things that the postdoc and I talked about was tracking these droplets. We're a little, they're getting cut off here. We would obviously need to back up a little bit. And so we have started to do some of that work. You saw there are like these really interesting satellite droplets. I wish it would let me. Yeah, there you go. These early satellite droplets are much smaller than the bigger ones. So it'd be really cool to have these, PDFs of the droplet sizes. I'm glad to hear you guys are interested. We also have side projects in AI for image processing. And so we also have students working on different ways of approaching image processing. So I'm not sure, this might be a really great way for us to come back and finish that. We started it and never really finished it for the study that we just published, or it's not published yet, sorry, it's in review. But anyway, I love that. We'll definitely look into that and try to publish on that. That would be really good. We have a lot of these data. I mean, just a ton from all different sizes of droplet impacts. So that hopefully would be really interesting and useful to your groups.
Yes, definitely. Just a side question on that. Is there any way in which you can use infrared cameras in this as well to actually see how the change of temperature of a droplet is?
Yes.
Is it not accurate enough?
In my experience so far, if I use water, infrared is not really great. It will tell me the external temperature really decently, but I have no idea what the real temperature is, especially for larger droplets. Maybe for smaller ones, you can assume they're the same temp all the way through, but I don't know. That's not something I've looked at before. But do you think that, are you saying that in the air, these droplets will change their temperature? Is that what you're saying?
Yeah, so when the droplet falls, particularly the small ones, their temperature drops very fast and quite a few degrees smaller. And there's one big question in tropical cyclone research, and that's whether or not these droplets actually contribute to the heat exchange. So usually during tropical cyclones, they grow in intensity because they get heat from the ocean and it goes into the atmosphere. And one of the open questions is if these droplets, so spray that's produced by breaking waves, whether or not that actually contributes at all to that. The problem is that we cannot really measure that, and heat. And in these pictures, we can actually measure the droplets, but not really the heat flux.
Right.
So if you would be able to answer something like that, I think that would really help out tropical cyclone research. So that's why I'm asking. Yeah.
That's a fantastic question. I have access to an IR camera, so I'll take a look and see what I can find. I don't know, Joey, maybe we could exchange email. I'll send my email address right here to everyone in case you want to send something. So maybe you could just quickly that, and then I can, I can take some data in the next few weeks or month and then maybe send you something and see if that would be helpful. Because we'd be super interested in that. That's a really good question. I don't know the answer to, but we could certainly try to do. I imagine the temperature gradient plays a big role too. So you probably get better results if we had slightly higher temperature gradients between the water and the atmosphere, right? I'm assuming that's one of the things that there must be happening in cyclones. But that's certainly something we could look at. I love this idea. It's really good.
Yeah, that would be fantastic. Yeah.
Yeah, I think it's a possibility for sure. I just have to look a little bit deeper, and maybe it's not AIR cameras. Maybe there's another way we can do it, but I'm sure we can figure out something.
Yeah, no, that would be amazing. I'll send you an email. Yeah.
Okay, great. That would be great. I don't know if you guys know Chanson. I'm trying to think, but he does a lot of work with jets into fluids, and I think he's from Australia.
Hubert Chanson?
Yes, that's right. Yeah. So in that synthetic aperture imaging thing I talked about earlier on, we were actually able to, I don't have it here quickly, but I was able to reproduce, using this camera system, I was able to reproduce Chanson's experiments, but without having to have measurements that were in the flow. They were in situ, you know, they were outside the flow. So this is kind of the same kind of thing. I think we could come up with something, Joey. I'm really excited. That sounds really good.
Yeah, it would be awesome. Thanks.
And it looks like
yeah, Leo has sent a message.
Yep, that's great. So maybe I'll just if you know Leo's email address, maybe you can send that to me, Vishal. I'd love to get in contact with them. But it sounds like they said even the prolate and oblate effects are still visible in their pictures. Yeah. Okay. Good.
I'll have to look. Tad, I don't know. I'll just check if
no worries.
have his email.
No worries. I can probably find it online as well. So I'll do that.
No worries.
Okay, thank you so much.
Right,
yeah,
great. That was very nice, very interesting, and thank you very much.